In the last class, we looked at some selected applications of transmission lines. Today, we shall see something which sort of removes something from a transmission line that we don't want. And what is that? Reflections. Yes. So as we mentioned, transmission lines are very prone to having two waves, one incident wave and a reflected wave. And we saw that the reflected wave can be there when the line impedance and the load impedance are not equal. So just to refresh a little bit, if I have, again let's assume a lossless line. If I have a line with characteristic impedance Z0 and I have a load impedance ZL, and I know that reflection coefficient at the load, that is gamma L, that will exist when ZL and Z0 are not equal. So this is something which we don't want, because the reflected wave goes back to the source and it can cause some loading or damage to the source, which is generally very undesirable. So now the question is, how can we reduce the reflection, or how to eliminate this reflection? So you can say, okay, if the Z0 and ZL are not equal, make them equal. That is one way. But many a time it so happens that the characteristic impedance is fixed by the engineer, whereas the load impedance is fixed by the client. Of course, there are applications where we can actually make Z0 and ZL, but this cannot be done for all applications. What if ZL is a load that is manifested by means of some other circuit? What if ZL is the impedance looking into some circuit like an amplifier or something like that, where it is not a physical single impedance but a function of multiple quantities? In such cases, ZL cannot be changed, but you can still change Z0. And what if ZL is complex? Can we make Z0 also as complex? Well, we can, but then this line would then become lossy, and that totally defeats the purpose. So there are times when we cannot change Z0, there are times when we cannot change ZL. So if somebody gives you a Z0 and a ZL which are not equal, and yet says that we want to eliminate the reflected wave, what to do? So let's take one case. Let ZL be real or purely resistive, and Z0 is also real. Now, let us say I have this line and I want to interface this to the load impedance ZL. Can I put some kind of a black box in the middle? Can I put a black box in the middle of Z0 and ZL so that when I am looking from this transmission line side, that is this side, this entire black box converts this impedance into Z0. So the input impedance looking from this end of this line looks like Z0. So even though the load impedance is actually ZL, this black box sort of tricks the transmission line into thinking that it is seeing a load of Z0, thereby making the reflection coefficient at this point 0. And that kind of solves our purpose. So what can we do to transform this load impedance ZL into a real impedance Z0? Even this is real. So I kind of gave you the hint by using the word called transformation. So therefore this black box is nothing but an impedance transformer. And the best example of impedance transformer is some transmission line. So therefore I know that I have to use a transmission line to transform this impedance ZL into Z0. So now suppose I have that transmission line and I say that suppose the black box or the impedance transformer is a transmission line having characteristic impedance Z1, where Z0 not equal to ZL not equal to Z1. The reason for this assumption will become clear in just a few moments. So now if I say this is my main line which I want to match, main line having impedance Z0 which I want to match to this load ZL, and I am connecting this intermediate piece of transmission line whose characteristic impedance is Z1. So one thing you can say right away, even Z1 should be real, because if Z1 is complex, then again this second transmission line will become lossy and again it defeats the purpose. So now let us look at this transmission line only. It is trying to transform this load impedance ZL into a real impedance Z0. So now let us quickly recap some properties of impedance transformation. If I have a real impedance at one end and I want to transform it to another real impedance at the other end, what should be the length of this line? The question is, what should be the length of this line? We have to remember, we have to find out what is Z1 as well as length, because this gives you a total solution. Simply knowing the characteristic impedance or simply knowing the length will not give you the entire picture. So coming back to the problem, after what distance does a real impedance transform back into a real impedance? I have two options, either L equals lambda by 2 or L equals lambda by 4. Here where the impedance repeats and here where the normalized impedance inverts itself, so still it is real. So now can I use lambda by 2? I cannot use lambda by 2 because if L is lambda by 2, this ZL will also look like ZL at this point. So therefore again there will be reflection. So therefore L equals lambda by 2 is not correct because it is giving us the same value of the impedance which we don't want. But what about lambda by 4? We can definitely look at that. So therefore, if I now define an impedance called Zin, that is the input impedance looking into this black box. So I can say, using the impedance transformation relationship, ZL will be transformed to what? Z1 times ZL plus JZ1 tan beta L divided by Z1 plus JZL tan beta L. Now over here, put L equals lambda by 4 and take these tan terms common, and this expression will reduce to Z1 square by ZL. So that means if I know, and if the input impedance looking into this black box is Z1 square by ZL, it should ideally be equal to Z0. This input impedance should be equal to Z0. Only then there will be no reflection. So this means that the actual value of Z1 that we want is nothing but the geometric mean of ZL and Z0. So if my black box is a transmission line of length lambda by 4, and characteristic impedance that equals the geometric mean of the line impedance and the load impedance that we want to match, then we can ensure that at this point the gamma will be 0, and that's it. Now what will happen at the load? That also you can think. So I leave it to you as an exercise to think whether any reflection will happen at the load and whether that will negatively impact Z0. So think a little bit on this. So this kind of a solution where we are using a lambda by 4 line to minimize reflections, this is called as a quarter wave transformer. Quarter wave means lambda by 4, and quarter wave transformer is also shown as QWT. Now here I am defining a terminology as the process or the technique or techniques to minimize reflections by trying to transform two impedances which are not equal. This technique is called as impedance matching. So we saw one case of impedance matching where both Z0 and ZL are real. Now let us see another case. Case 2, Z0 is real but ZL is complex. So now we have a bit of an issue. Can we use the quarter wave transformer? Well, if we use the quarter wave transformer, the value of Z1 will come out to be complex because ZL is complex. So again, Z1 becomes a lossy line and our purpose is defeated. So we cannot use quarter wave transformer. So, is there any way to approach this? Well, there is. There is a very popular technique, but before we discuss that, we need to look at some basics. Let us define some things before we address the larger problem at hand, that is matching a complex load impedance. So, let us look at some terms which we know. We know about resistance. Now, what is the reciprocal of resistance? Or what is 1 by resistance? It is nothing but conductance. So if resistance is denoted as R, conductance is denoted as G. What about reactance? What is the reciprocal of reactance called? If reactance is denoted as X, then 1 by reactance or 1 by X is represented in using a term called susceptance. And we generally call this as B. Impedance, which we write as Z, its reciprocal. Its reciprocal is called admittance or Y. So what we have, G is 1 by R, B is 1 by X and Y is 1 by Z. So now we know how to use the Smith chart using impedance values or the normalized impedance. We know how to use the Smith chart using the normalized impedance values. But there are many applications, and we are going to see one of them very shortly, which is going to help us in solve this problem. And that is to use the Smith chart with admittance values rather than impedance. So we know that the transformation relationship for normalized impedance onto the gamma plane is nothing but gamma equals small z minus 1 by small z plus 1, which is nothing but the normalized impedance terms. So now if I express this in terms of admittance or normalized admittance, I can write 1 by small y minus 1 divided by 1 by small y plus 1. So even in terms of admittance, the normalized relation still holds. So what do we have over here? We get 1 minus y by 1 plus y. Now I can obviously rewrite this expression in this form. Y minus 1 by y plus 1 with a minus sign. Or if you want to write it in a phasor notation, I can write y minus 1 by y plus 1 having a phase of pi, because that will give you the minus sign. Now what we see is this z minus 1 and z plus 1, and here also I have y minus 1 by y plus 1. It is exactly the same, but with a phase angle of pi. So therefore, if I have this Smith chart, and we know that all the coordinates are based on impedance, what I can do is I can simply invert the Smith chart by 180 degrees to account for this pi, and then simply use these coordinates as normalized admittance values rather than impedance values. But rather than doing that, because again inverting the Smith chart would open another can of worms, and this would cause unnecessary confusions. So rather than doing that, is there a way I can still keep the Smith chart upright yet use the coordinates as admittance coordinates? I can. So let's see how. Let's see how. So as we know, the Smith chart is on the gamma plane, and we had defined the gamma plane as u plus jv. So this is one of the R circles. So what we have proved that the relation for gamma for both normalized impedance and normalized admittance is the same, except that there is a 180 degree phase shift somewhere. So if I keep my Smith chart circles upright, but I invert my u and jv axis, then what? So then this becomes plus u and this becomes plus jv, whereas the rest of the Smith chart remains unchanged. So rather than inverting the Smith chart, I am inverting the axis. But notice that on the Smith chart, the u and v axis are not visible. So in some sense, what was jv over here and what was u over here, we have now put plus u over here and jv along here. That is something which you have to visualize. So if you want, you can draw the axis, nothing will stop you. But in the Smith chart, in the form that it comes in, these axes are not labeled. So here we have z coordinates, and here it becomes again gamma plane, or I should say minus gamma plane, and this becomes y coordinates. So now what changes? So if you notice, this used to be the short circuit point, and this used to be the open circuit point on the z plane or the z Smith chart. Now on the y Smith chart, let us take a look. Now all of these markings have become admittance markings. So now if you notice, the real axis was saying earlier resistance component or conductance component. So now since we have a y Smith chart, these real axis will now become conductance. whereas the upper circumference was earlier called as inductive reactance, but now since we are looking at Y values, it becomes capacitive susceptance. So all the capacitance values will now come over here. Likewise, this lower periphery will become inductive susceptance. Now these are Y values. Now at this point, Y becomes equal to 0. That means the admittance is 0. So that means now that since we have inverted the axis, Y is equal to 0 now means open circuit. And infinite admittance means it's a short circuit. So this is one change. The other change is a small change, but rather something that is very important. Suppose we have some impedance Z1 whose reflection coefficient we want to measure. We already know how to measure the reflection coefficient by drawing the VSWR circle, but for the phase we take it as phi L, that is with respect to the plus U axis. But now if I have some impedance over here or admittance Y2 and I want to measure its reflection coefficient, it has to be with respect to the positive U axis. So this is now phi. That is the only change, because both phases are with respect to the plus U axis. So now with this backdrop, let us address the issue at hand. And what was the issue? Matching a complex load to a lossless line. Matching a complex load to a lossless line. So now let us say I have this line Z0 and I want to connect this complex load impedance ZL. What I will do is I will first convert this into the normalized admittance. So I can convert this into normalized impedance, small ZL, that is nothing but ZL by Z0, and load admittance YL is nothing but 1 by small ZL. So let's say I have the normalized admittance as YL. So the normalized characteristic admittance of this line will be what? It will be 1. Same as characteristic impedance. Now, what I want that the input impedance looking at this point or this end of the main line should be equal to Z0. That means the small y in should be equal to 1. The normalized admittance looking into this side should be 1. Only then at this junction I can say that there will be no gamma or the gamma will be 0. So what I will do, I will continue this line of impedance Z0 or normalized admittance 1 such that this YL or the small YL transforms into an admittance. Let me call this as YL prime or the YL transformed. That is something of the form of 1 plus J times small b. Why we are doing this is because at this point we are transforming this impedance into some impedance whose real value becomes 1. So the half the matching problem is done. Now all we need to do is to take care of this JB. If I were to somehow introduce a compensating element of admittance minus JB and I add the two, then plus JB and minus JB will cancel out. So this distance is called as ds, or the distance from the load where the transformed admittance, the real quantity, becomes 1. Let the imaginary part be anything. Okay, the meaning of S I shall tell you very shortly. Now pay close attention. What I am going to do over here is to introduce an element whose admittance is minus JB. I am introducing another piece of transmission line. Okay, I am introducing another piece of transmission line whose characteristic impedance is also Z0, but its load is a short circuit, and this line is being introduced in parallel to the main line, but at this point. So this transmission line, which is added additionally and whose load is a short circuit, can be even open circuit. So this kind of additional line which is added in parallel is called as a stub. Let me repeat, the additional piece of transmission line that is ended with a short circuit or even an open circuit and added in parallel to the transmission line is called as a stub. So therefore, if this is a short circuit, it will get transformed to some impedance or admittance. So therefore, let's call this admittance as Y stub or small y stub. Now what do we know? We know that from the Smith chart, if your load impedance is a short circuit, then the impedance at any point on the line will be purely imaginary because you will be moving at some point on the outermost circle. Therefore, R will be 0. Okay, so I can say now that at the junction, which junction? Junction of line and stub, I have two admittances. One is YL prime, that is nothing but 1 plus JB, and Y stub. I want this to be equal to minus JB. So therefore, the length of my stub LS should be such that I get Y stub equal to minus JB. LS means the length of the stub and ds means the distance of the stub from the load, the main load which you want to match. So at this junction, if I have these two admittances in parallel, what will be my net Y in? Y in will be nothing but YL prime plus Y stub, because as you know, in a parallel combination, The impedance, I can say, is nothing but the sum of the reciprocals the impedance is nothing but the sum of reciprocals. So that means the admittances would be a direct addition. So that is why rather than using impedances and having all these reciprocals come into picture, we use admittance values. So therefore, if I now add these two in parallel, what will I get? Yin will become exactly 1. And we are done. So this 1 plus JB and minus JB will cancel out, and the line at this junction will see a net admittance which is equal to 1. And that's it, we are done. Because Yin equals to 1 means the line is seeing an impedance which is equal to Z0 or Y0 or whatever you want to call. Okay. So you can find out. So the solution for the impedance matching using this stub is when you know the values of DS as well as LS. Okay. So let us now see how to do this using a Smith chart with an example. Suppose I have given you a line which has load impedance 50 ohms. Sorry, a characteristic impedance 50 ohms. Load impedance, let us say it is something of the form 60 plus J60 ohms. Now I want to design a stub network to match this. So first step is to find the normalized load impedance, which is nothing but ZL by Z0, which is 1.2 plus J1.2. Sorry, let me just make this minus. There's a reason why I'm doing that. So this will become 1.2 minus J1.2. So what will be YL? YL is nothing but 1 by small YL is nothing but 1 by small ZL. So just have to do a little bit of manipulation. So this is nothing but 1.2 plus J1.2 divided by that is 1.2 plus J1.2 divided by 2.88. Okay, so just for the sake of simplicity, I can say that YL will be of the, if you can just approximate 2.88 to 3. Don't do that if you have a calculator, but I don't have one with me right now. So I'm just approximating YL as 0.4 plus J 0.4. Just to make things simple. So now let's get to business. Now we are using this Smith chart as an admittance chart. So all the coordinates are now admittance. So where will YL lie? Since we are using admittance, YL will be nothing but the intersection of the G equals 0.4 circle and the B equals 0.4 circle. Remember, now it is conductance and susceptance, not impedance and not resistance and reactance. It is conductance and susceptance. So 0.4 conductance is here, 0.4 susceptance is here. So this point is my small YL. So now Let me take my compass and draw the constant VSWR circle. Very good. So I can draw one line connecting the center to the periphery. Okay, so now how do I proceed? So I have to move away from the load. So moving away from the load would mean what? Clockwise or anti-clockwise? Would the direction change when I am changing the coordinates to admittance? No, it will not change. Because you are just inverting the axis. The direction of rotation remains the same. So again, like the case of impedance, I shall be moving clockwise. Now I shall be moving away from the load until I reach this point. 1 plus JB. So 1 means I am looking at this circle. This is the G equals 1 circle. This circle, which passes through the center of the Smith chart. So I will continue moving until the VSWR circle hits the G equal to 1 circle, and this happens at this point. So therefore, this is YL prime. So again, I am going to connect these two. So I really don't care about the value, because what I need, I'm more interested in is the distance between these two. So what we proved, or what we started with, was when I'm moving from the load to the point where I'm getting 1 plus JB, this is ds. So if you now take a look at the wavelength readings or the wavelength towards generator, so this is of the order of, this point is 0.168 lambda, and this point is roughly about 0.07 lambda. So the distance between these two will give us ds. So 0.168 minus 0.07 would be roughly 0.098 lambda. So this is the distance from the load where the stub must be placed. Is this clear? This is the distance from the load at which the stub must be placed. So now we need to move to the second part of the problem, that is the stub admittance. We want the stub admittance to be minus JB. So here what you can see, JB is nothing but roughly about 1.15. So somewhere over here between 1.1 and 1.2 of the J circles. So now if I want minus JB, I have to look at these 2 points, or let's say somewhere over here in the middle. It's a rough solution, but nonetheless. So this is the value of JB that I want. So here YL I can write as 1 plus J 1.15. That is why this is coming out to be minus 1.15. Now we have defined that our stub will be short circuit. So on the admittance chart, where is short circuit? It's over here. Short circuit, infinite admittance. So somehow I from the short circuit and move away from the short circuit or the load and reach the point where I get Y stub equals minus JB. I must start from the short circuit end and keep moving away from this short circuit load until I get minus JB. So on the Smith chart, my starting point is here and I have to move along the outer periphery this way. Let me mark this also just in case. Until I reach this point. So all I need to do is just see the difference in distance between this point and this point. So whatever this is, this will give me the length of the stub. So if I'm starting at 0.25 and I'm ending at 0.364, my LS will be 0.114 lambda. Because remember, I'm moving away from the load. That's it. So I need a stub of length 0.114 lambda placed at a distance of 0.098 lambda from the load. And that's my solution. So with this, we finish the discussion on the topic called impedance matching. However, there are plenty more techniques for impedance matching which are beyond the scope of this course. And impedance matching is a very, very important problem in transmission lines. If any of you are interested to take this up further, I recommend you do an advanced course on RF and microwave engineering. So with this, we shall stop today. Thank you.